All right, let's dive right into this explainer and set the stage for, honestly, one of the most fascinating magic tricks of the modern era. We're talking about how our digital world fundamentally keeps secrets safe from prying eyes. Whether you're just firing off a quick text, logging into your bank account, or buying something online, there's this silent, incredibly complex mathematical battle happening right beneath your fingertips to protect your data.
So I want you to really think about this for a second. How does a secret stay hidden on the open internet? It's kind of a wild concept, right? Imagine the seemingly impossible task of sending highly sensitive data across a completely public network. A network where your information is literally bouncing through public Wi-Fi routers, global fiber optic cables, and these massive data centers, and somehow it doesn't get intercepted and read. It's like trying to pass a sealed, completely transparent envelope through a crowd of 1,000 people, just crossing your fingers that nobody looks at the letter inside. But we do it billions of times a day. How?
Well, to answer that, here is our roadmap for today. First up, unlocking asymmetric cryptography. Second, how RSA encryption works. Third, the elliptic curve evolution. And finally, the big showdown, RSA versus ECC.
Okay, Chapter 1. Unlocking Asymmetric Cryptography, the Foundation.
Now, before this foundational shift happened, if you wanted to send a secret, both you and the receiver had to magically secretly share the exact same key beforehand, which is, a massive headache. Asymmetric cryptography totally solved this. It's basically a process that uses a pair of mathematically related keys to encrypt and decrypt a message. Crucially, one of these is a public key and the other is a private key. Think of the public key like an open padlock that literally anyone in the world can use to snap shut and lock a box. But once it's locked, that padlock can only be opened by the completely different, entirely secret private key held by the intended recipient.
Let's put this public directory concept into a real-world scenario with, say, Mary and Roy. Mary wants to send the message, "Meet me now," to Roy. She doesn't need to meet Roy in some dark alley to exchange a secret password. No way. She simply looks up Roy's public key in a public directory, because anyone can see it, and she uses it to lock her message. Instantly, the text scrambles into total gibberish. That ciphertext then travels across the open internet, and even if someone intercepts it, it is totally useless. When it finally reaches Roy, he just uses his own secret private key to unlock it and read, "Meet me now." The keys are paired together, but they are completely distinct.
Of course, every brilliant system has its pros and cons. The advantages here are absolutely revolutionary. It completely eliminates that whole key distribution problem we just talked about. Plus, it enables digital signatures. This means if a sender locks something with their private key, anyone can unlock it with the sender's public key. That proves absolutely that the message came from them, enabling what we call non-repudiation. Basically, the sender can't deny sending it. But there is a catch. It is a mathematically heavy, much slower process compared to older symmetric cryptography. Because of that sluggishness, it's just not practical for encrypting massive bulk messages all at once. Moving right along to Chapter 2, how RSA encryption works, the legacy standard.
So let's look at RSA. Introduced back in 1977 by Revis, Shamir, and Adelman, it relies on 4 foundational steps. First, the system chooses 2 incredibly large prime numbers. Second, it multiplies these primes together to create what's called the modulus and uses that to mathematically generate your public and private keys. Third, your data is encrypted using that public key. And finally, it's decrypted using the private key.
The absolute crucial point here is that RSA security relies entirely on the computational difficulty of factoring massive prime numbers. Let me explain why this is so brilliant. Multiplying 2 huge primes together, super easy for a computer to do. Just a fraction of a second. But taking that massive resulting number and reverse engineering it, trying to figure out exactly which 2 original primes were used to create it, that is overwhelmingly difficult. The time needed to factor the product of 2 sufficiently large primes is literally beyond the capabilities of most attackers. It's a one-way mathematical street. And this classic 1977 mathematics is absolutely everywhere today. It's embedded in SSL and TLS, that little secure padlock icon you see when you're browsing a website. It's also used heavily for digital signatures and hashing to ensure data hasn't been tampered with. To keep all this secure, RSA utilizes incredibly long keys, typically 1024 or 2048 bits long. And actually, because modern computers are getting so insanely fast, experts now strongly recommend those 2048-bit keys, just to guarantee that attackers can't brute force factor those prime numbers.
All right, Chapter 3, the elliptic curve evolution, the modern upgrade.
So, jump forward to 1985.
Neil Koblitz and Victor Miller introduced this brilliant shift in methodology. We're no longer just relying on multiplying prime numbers. Instead, we are looking at the geometric mathematics of an elliptic curve, plotted over finite fields. It's defined by the equation y squared equals x cubed plus ax plus b. Now, I know that sounds abstract, and the looping shape on a graph looks a bit complex, but it allows for a totally different and frankly amazing kind of cryptographic magic.
Let's break down how this works using a classic example with Alice and Bob. First, Alice and Bob publicly agree on a starting point on that curve. Let's just call it point G. Second, they each secretly pick a private number. Alice takes her private number and performs what's called scalar multiplication. Basically, she's taking a specific number of geometric steps, bouncing around the curve to land on a new point. Bob does the exact same thing with his secret number. Third, they swap the points they landed on. Those are now their public keys. Finally, Alice takes Bob's public point, applies her secret number of steps to it, and Bob does the exact inverse with Alice's point. And here is the magic trick. Because of the special properties of the curve, they both arrive at the exact same shared secret coordinate on the graph, without ever exposing their initial private numbers.
So, what actually makes this secure? It's something called the elliptic curve discrete logarithm problem, or ECDLP. Even if an eavesdropper can see everything public, the public curve, the starting point, and the endpoints Alice and Bob swapped, working backward to figure out the exact number of steps they took to get there is computationally infeasible. With current technology, there are simply no known shortcuts to break this encryption. It is an impenetrable mathematical wall.
Because it is so incredibly secure and highly efficient, modern tech leans heavily on ECC. Since it requires way less computing power and memory than RSA, it's the absolute ideal choice for the Internet of Things. Think about your smart home devices, sensors, or smartwatches that have very little battery life. It is also the backbone of secure wallets and cryptocurrencies and blockchain. Oh, and it enables much faster secure web connections for our mobile devices. It's a real game changer.
Which brings us to Chapter 4, RSA versus ECC, the showdown.
Contrasting these two methods really makes the future clear. RSA relies on prime factorization, while ECC uses the mathematics of elliptic curves. Status-wise, RSA is well established, it's faced decades of scrutiny, but it's arguably heading toward the end of its tenure. ECC is newer, highly secure, and expected to scale up massively. Now, interestingly, RSA can sometimes run faster purely because of its mathematical simplicity, whereas ECC's complex nature requires a tiny bit more time. But the massive differentiator, the absolute deal-breaker here, is the key length.
The sheer numbers required to run these algorithms are, well, shocking. To achieve a 112-bit security level, RSA needs a 2048-bit key. ECC, only 224 to 255 bits. And for robust 256-bit security, RSA requires an absolutely massive 15,360-bit key.
Let me just explicitly hammer home this drastic difference to really lock in that aha moment. To achieve the exact same 256-bit security level, RSA requires 15,360 bits of data. ECC requires just over 512 bits. That is exactly why ECC is the future. It drastically reduces bandwidth consumption, requires vastly less storage, and saves an incredible amount of computing power and battery life compared to RSA, all while keeping your data just as safe, if not safer. And that brings us to the end of our journey today. But really, it's just the beginning of the next chapter. You see, cybersecurity is a constant, unending, evolutionary arms race. We've gone from the burden of sharing single passwords to the genius of prime factorization with RSA, all the way to the elegant geometric curves of ECC. As technology continues to evolve, especially with the looming, code-breaking shadow of quantum computing on the horizon, what will the next generation of cryptographic evolution look like? It's a thrilling question. Thanks for joining this explainer, and keep your secrets safe.